Hey guys, so today we're going to be dealing with implicit differentiation. Implicit differentiation is a topic that can come off as really hard or really easy, just depending on your teacher and your exposure to it. It's also, a topic that is very important because there are two very important applications that come out of implicit differentiation, and I'm not talking about word problems, but actually uh, they're very important because you need to know implicit differentiation in order to take the derivative of certain types of functions. And I'm going to talk about that in this video as well. So let's get into it. So what is implicit differentiation? Well, so far in our calculus journey, we've seen functions, written explicitly, y is written explicitly in terms of x. Like here, y equals ln x. Y is written explicitly in terms of x. I can clearly see what y is equal to. Stuff like this, y is equal to cosine x, y is equal to x cubed plus 2x plus 1, stuff like that, where you got y isolated on one side and x on the other side of the equal sign. So it's very clear what y is equal to. And that's basically, y being explicitly written in terms of x. Well, what do I mean by an implicit function, though? This is more explicit, but what do I mean by implicit? Well, let me just erase this. I'll show you guys what an implicit function is, and I'll start off with something you've seen before. You've seen some implicit functions before. So let me show you one. You'll recognize. The equation of a circle is an implicit relationship between x and y. You don't see x, you don't see y written explicitly in terms of x, something like this as well. This is a very famous one. Type this in Desmos and see what it comes out to. It's actually a very famous one. This is also an implicit function. You don't see y written explicitly in terms of x. So informally, you can think that, you can think of implicit functions as functions where x and y are found together on either one or both sides of the equal sign. So as we see here, x and y are both found on the left side of the equal sign. In this one, x and y are found together on both the left and right side of the equal sign. So basically, if you have a function where, x and y are found together on, at least one side of the equal sign, you could think of that as implicit. That's just a very informal idea. So, well, what about implicit differentiation? Well, sometimes we want to take derivatives of functions like these. And, as we've seen before when we had something like, y equals ln x, when we took the derivative of this, y prime, well, we took the derivative of the left side and we got y prime. And, derivative of the right side, 1 over x. And like I said, this is written explicitly, so y is already isolated for you. Now, when you get something, written implicitly, like the following right here, it's sometimes very hard. It can get very hard to isolate for y, to get it on its own. A computer system could do it fairly easily. However, by hand, and sometimes it can just get really complicated. Like this would be pretty easy to isolate. I haven't tried isolating this one, but from the looks of it, I don't think it's going to be, a simple two-step thing. So it can be hard to isolate for y. So in order to take the derivative of implicit functions, well, we need to understand implicit differentiation. And it's best to learn implicit differentiation through example. So I'm going to start with our first example. And in this example, what I'm going to do is we're given this. Sine of x squared plus y is equal to xy. Now, what I want you to remember is that, we had, like I showed you before, y is equal to ln x. In order to take the derivative, we took the derivative on both sides. So when we took the derivative on the left side, Oh, sorry about that. When we took the derivative on the left side, we got y prime. Took the derivative on the right side, we got 1 over x. So y prime, which is dy by dx, is 1 over x. So I want you to keep that in the back of your head. So treat y like a variable. So let's get into this. So in order to find y prime, that's what we're looking for. Find y prime. In order to find y prime, well, we're given a function like this, and let's take the derivative on both sides, obviously. So let's start with the left side. So taking the derivative, you need to use the chain rule here, and I'm just going to do that really quickly. So we got cosine x squared plus y times, well, taking the derivative, what's the derivative of x squared? Well, it's just 2x, plus, taking the derivative of y with respect to x, well, what is that? That's just dy by dx, and that is just y prime, right? dy by dx is equal to y prime. So we got y prime right there. And this, now we take the derivative of the right side, so this part. So let's do that. So taking the derivative of that, well, because x and y are both variables, we have to use the product rule. So let's do that. Let's use the product rule. So let's take the derivative of x first. So what's the derivative of x? It's just 1. So it's 1 times y plus x. Now taking the derivative with y with respect to x, well, we just get y prime. So there we go. Now we want to find y prime, right? Like we have y prime in the equation, but now we want to isolate for it. And this is pretty easy, so I'm just gonna simplify this, write everything out. So we're gonna isolate for y prime. So what we're gonna do now is we are going to multiply this out. All right. This is something you should always do at the end, is that you have to obviously write y prime in terms of everything else. And so let's multiply this out. So we got y prime is cosine x squared plus y is equal to y plus prime. And so let's get the just isolating. So we got xy prime. We have minus y prime times cosine x plus y. So we can factor out the y prime on the right side. And I'm just going to erase all of our other work up here. So what you're seeing is that, you got to treat y as a variable. And, when you take the derivative with respect to x of y, it's just y prime, right? It's dy by dx, which is also y prime. You can write dy by dx if you like, but, y prime makes it much neater than writing dy by dx. It's also much faster. So just going to continue this here, and then I'm just going to move to the top. So we got cosine x squared plus y minus y is equal to y prime x minus cosine x squared plus y. So moving up here now, just going back to the top for more space. The answer, dividing both sides by, in brackets, x minus cosine x squared plus y, we get 2x cosine x squared plus y minus y divided by x minus cosine x squared plus y, and that is y prime. This is our answer. So, like I said, implicit differentiation can either come off really hard or really easy. And honestly, it's just not that bad. You just got to make sure, you got to understand what implicit functions are. I gave you guys that really good informal idea that if you see, x and y together on, at least one side of the equation, the equal sign, then, you got an implicit function. And that's a very good rule of thumb. So here we had an implicit function. We took the derivative of both sides, and then we just isolate. So it's a matter of realizing, dy by dx and all that. So let's do another example. This one's a little harder. So actually not too much harder. It's actually not that bad. Maybe actually easier. I don't know. You guys decide. So I got x squared plus y squared is equal to 25. This might just be easier. And I gotta find y prime. Find y prime. So let's take the derivative. Well, we realize this is an implicit function because we got x and y together on at least one side. So taking the derivative now, well, taking the derivative of the right side first. Well, what's the derivative of a constant? It's just 0. And taking the derivative of the left side, so 2x, this is just using the power rule, plus, well, now we also have to, use the power rule because y is also a variable and take the derivative with respect to x. So we bring down the 2 and we get y, but we have to take the derivative of y also. So we got to do y prime. So it's 2y times y prime. We got dy by dx. So, this is kind of like the chain rule right here, where you bring down the 2, you get 2y times y prime. Now, in contrast to what we had on the last slide, y did not have any power anywhere, did not have any exponent to it, right? So when we actually did bring down an exponent when we had y here on both sides. We had y to the power of 1. Well, we bring down the 1. This is 0 now, right? Times y prime. Let me write that better. That looks kind of ugly. So when we took the derivative here of y, what we had was we had y to the power of 1. We brought down the exponent, and we had, we had 1 y to the 0 times y prime. This turned out to be 1 as well. So we just wrote y prime. We didn't write that, the initial stuff at the front. So let's go back. So basically, you brought down the exponent, you have 2y times y prime. And you could think, when you had x, right, you brought down 2x. Then you took the derivative of x with respect to x, and that's just going to be 1. What's the derivative of, x? It's just 1. Right? So, be very careful about that when you have exponents or stuff on, y, that, you bring down the exponent. You got to use the chain rule here. And this is a very important application of the chain rule. And students, they miss it. They sometimes just do this. They say, oh, 2y prime. Don't do that. That's wrong. You forgot the y. Just y and also y prime. So now let's isolate for y prime. Well, this isn't too bad. Well, we got 2y times y prime is equal to negative 2x. And y prime is just negative 2x over 2y. We've done our job. We've isolated for y prime. You can simplify if you want. Cancel the 2's. Just negative x over y. There we go. So this question, it really highlighted that you need to be aware when you're taking the derivative here that you got to use the chain rule. And it's not the same, like here. Here we had x squared. Took the derivative, 2x. And, you could think of the chain rule here as well. You got 2x, you took the derivative. And, well, you brought down the exponent, you took the derivative, and then, you you take the derivative of the inside. If you put brackets around here, take the derivative of the inside. Well, what's the derivative of x on its own? It's just 1, but we just don't write the 1. Here, the derivative of y with respect to x is y prime. Here, we took the derivative of x with respect to x, and here it turned out 1. So you need to be aware of that. Very, very aware of that. So, I don't know, maybe I should explain that again. Let me explain that maybe using a different example. So 2x squared, actually wait, x squared plus y squared is equal to 4. Basically the same thing. So we had x squared, right? So let's take that derivative of x squared. Let's put everything in brackets first. So you get bracket x squared plus bracket y squared is equal to 4. Take the derivative on both sides. So let's do this. We know the derivative on the right side is 0. So what about the left side? So let's bring down the 2. Let's use the chain rule. Bring down the 2. Got the x in the brackets. We just got 1 here. Well, we took the derivative, on the outside. Now let's move inward like we did in the chain rule. So what's the derivative of the inside in the brackets? What's the derivative of x with respect to x? Well, it's just 1. So it's times by 1 plus. Now let's use the chain rule here as well. Bring down the 2. We've got y in brackets. Now let's take the derivative of what's inside the brackets. What's the derivative of y with respect to x? Well, it's just dy by dx, and dy by dx is just y prime. So I hope that makes more sense there. That's basically what we did. So that's basically what implicit differentiation is. It's just treating y as a variable and you're just taking the derivative of it, of an implicit function, where you find x and y on at least one side of the equation together. So let's go on into those two important applications I talked about earlier. Well, we just did some implicit differentiation, and it turns out, there are two there's two types of functions that, you need to know implicit differentiation in order to take their derivatives. And these are let me erase that. These are exponential functions. And inverse trig functions. Very, very, very important. These two rely on implicit differentiation. These are, you use implicit differentiation, you're usually dealing with these two, especially the latter one. So let's do an example. And we're going to do an example of, using the exponential functions. So we're going to have a function y is equal to 2x. This is written explicitly. However, to take the derivative, we must use implicit differentiation. So you pay attention here. You actually have to use implicit differentiation to take the derivative, and you'll see why. So, well, how do we take the derivative? Well, we got x, up here. X, the exponent. Well, you know what we could do? We could take the ln of both sides. Why are we taking the ln of both sides? Because if we take the ln of both sides, going back to our logarithm rules, we can bring down the x. Now we have no more power to deal with, right? And I talked about these in the power rule video, these exponential functions. And, they're not taken, you don't take the derivative by, bringing down the exponent and then minusing 1 like we did with, something like this. Taking the derivative is not the same method. So let's continue. So we got ln y is equal to x ln 2. These are the same, right? We're not taking the derivative yet. We haven't even started. Well, now let's take the derivative. Well, we notice something. Is that y isn't, on its own. It's got something acting on it. It's got this, it's ln y is equal to x ln 2. So what do? Well, it's not exactly explicit because we've got something acting on y. So let's take the derivative on both sides again. So let's do the right side first because that's easier. So what is the derivative here? Well, we just have ln 2, which is just some constant, and we have x. So taking the derivative, well, this is just ln 2 because the derivative of x is just 1. So we're just left with a constant. So now let's take the derivative on the left side. Well, like I showed you before, let's take the derivative. Well, we have to use the chain rule. So we get 1 over y, because we have to take the derivative, and we got to use the chain rule, times y prime. Just as I showed you in example 2, like here. We use the chain rule, 1 over y times y prime. Because something's acting on y, we have to use the chain rule, so we gotta take the derivative, and then we have to take the derivative of y itself with respect to x, and that is this part. So we took the derivative of the function, then derivative of y with respect to x. So now we got y prime. Now let's isolate for y prime. Y prime is equal to y ln 2. We're not done yet though. What is y equal to? Well, y is right at our start. Y is equal to 2 to the x. So what is y prime equal to? Well, substitute 2 to the x and for y, we just get this. We're done. We took the derivative of an exponential function. That is our first application. Now, I also talked about another application, and this one troubles students a lot. Students struggle with this. Teachers, they like to have you memorize identities sometimes for this. However, there's a better way using implicit differentiation, which doesn't require memorization. You just gotta, understand the process, and it's honestly much easier than trying to memorize identities and trying to find the derivatives, or just memorizing the derivative on its own and then trying to tweak it depending on the question. And I've seen students do that, and it's a very tedious. It's probably a lot of students, it's the bane of their calculus career, is that dealing with inverse trig functions. I'm going to do a separate video on this as well. Going through inverse trig functions. But here I'm going to do y is equal to inverse sine x. And the students, this is one thing they hate in calculus, is inverse trig functions. So, well, how do we take the derivative of this? Well, in one video I showed you guys, reciprocal trig functions and trig functions, but I did mention at the end that inverse trig functions, they require implicit differentiation. And now that we've learned implicit differentiation, we can deal with these. So, well, how do we go about this? I probably mentioned that at the start, that teachers like to test this because it requires a little more thinking, and they do. So, well, you know what we're going to do? We're going to take the sine of both sides. So we're going to basically undo the inverse sine on the right side. So by doing sine, well, this just turns out to be x. Well, looking at this statement, what do we notice? Well, look at this statement closely. Think about a triangle. And I noticed this, what students do a lot is that they kind of disconnect ideas. They think they're doing calculus and they forget other mathematical ideas, which are very important. And here's one important realization that, it might be obvious to some, but usually isn't. Is that, you got sine y. Y is some angle. and x is some side length. So let me draw a triangle, a right triangle. Y is my angle. So I'm just going to, I always pick this angle. So you can say this is y, this is my angle. It's arbitrary, kind of. So y is my angle. Well, sine is the relationship between the opposite and the hypotenuse. Well, I just have x here. Well, x is divided by 1, right? I can write that, x divided by 1. We just don't write the 1 commonly. So I can say this is just x divided by 1. Actually, I'm going to write that like this. I can just say this is x divided by 1. And sine is the relationship between the opposite side and the hypotenuse. So I can see this is my opposite side and this is my hypotenuse. So let me tweak this triangle then. This triangle comes to be, this is y. If my opposite side is now x and my hypotenuse is 1, well then I can figure out my adjacent side because this is a right triangle using the Pythagorean theorem. It's just 1 minus x squared all under the square root, right? Just using the Pythagorean theorem, a squared plus b squared equals c squared, and then we just, rearrange, and we get the adjacent side. So now I got all sides of the triangle, and my angle is y. I'll tell you where this comes in use in a bit. So rewriting this, sine y is equal to x, and x is over some imaginary 1. So let's take the derivative. Let's take the derivative of this. Take the derivative of the right side and get cosine y, and because of the chain rule, cosine y times y prime, and taking the derivative of the right side, the derivative of x with respect to x is just 1. So there we go. Now let's isolate for y prime. Do that. So let's isolate for y prime. Let's do it up here. So y prime is equal to 1 divided by cosine y. We're almost done. So dy by dx, y prime, is equal to 1 divided by cosine y. Well, what is cosine y? Remember, y is just an angle. Let's refer to the triangle. The cosine is the ratio between the adjacent and hypotenuse. Well, what's the adjacent side here? Y is this angle. What is the adjacent side? Well, the adjacent side is this, right? And the hypotenuse is this. So let's substitute that into the equation. So y prime is equal to 1 over the adjacent divided by the hypotenuse. What's the adjacent side? The adjacent side is 1 minus x squared divided by the hypotenuse, and the hypotenuse is just 1. So we got 1 divided by, put this in brackets, 1 minus x squared all square rooted divided by 1. And well, just knowing your algebra, this just turns out to be 1 over 1 minus x squared. There we go. We got our answer. Y prime is 1 over 1 minus x squared, all square rooted in the denominator. So 1 divided by square root 1 minus x squared. That's our derivative. Done. I will do another video on this and give you more explanation now that you guys understand the implicit differentiation and how to take the derivative of inverse trig functions, because students really struggle with this. And here you saw we used no identities. We just we used our triangle, and the triangle always work. The triangle method, it's not something that's usually taught by teachers, but it's a much better method because it doesn't require any memorization. You just, it just requires understanding that, you got this triangle, you got these side lengths, you draw it and you get this visual image and you use that to, take your derivatives. And it's really cool, it's really easy. And I'll be talking about it more in a video on just taking the derivative of inverse trig functions. So thanks for watching, guys. Hope you guys enjoyed. Like and subscribe.